an image that consists of different regions of a different structure. And this could be, for instance, a crystal image like here, which is from electron microscopy applications. So here the notion of structure would be pretty strict. It's piecewise periodic in the ideal setting. But it could be also a little bit more loose, like in textures. But as far as our application is concerned, structure could be really anything as long as there is a suitable feature extractor, so a function that maps any pixel in the image to a feature vector, which can encode this kind of structure that you're interested in discriminating. And for instance, for textures, often Gabor histograms are used to give you a sense. And now the task, of course, is to find the best labeling function or segmentation. And in this work, we are tackling the problem from the point of view of variational methods, which is a very powerful mathematical tool to directly find for the best function in an infinite dimensional function space of the admissible labeling functions. And so typically you design an energy function, which is a functional action acting on an infinite dimensional space. So the argument u here is an infinite dimensional function, the labeling function. And often these functionals are then comprised of two terms. One is the fidelity term, which measures how well your current labeling fits to the data. So here we penalize if the feature at a certain position deviates from the mean feature of the corresponding region. And this steers the segmentation that we multiply with this difference towards 1 for the correct region and towards 0 for the incorrect regions. But then there is also a regularizing term, and this helps us to regularize the solution. So in this case, we penalize the total variation of the segmentation, or in other words, the length of the region boundaries. And this helps to directly suppress labeling noise. So with this lambda that's in front of the total variation, which is a scalar parameter, you can directly steer the smoothness of the resulting solution. The problem, however, in this application is if we want to do this in an unsupervised fashion, we don't know these mean features that we would like to put into the fidelity term. And in a high-dimensional setting, it's maybe not so easy to retrieve those, but an initial guess might be computed using k-means, but still in high dimensions there are problems. So we propose to first compute the feature matrix and perform a principal component analysis to project onto a lower dimensional space, which should work well since we are only searching for a few regions, so there should be a lower dimensional representation if the features are very good and don't have high inner class variance. And then we can perform k-means clustering on the projected coefficient space and get the cluster means in this lower dimensional space. And now the nice thing for this region indicator is that we can plug in both the coefficients and the clusters in the lower dimensional space and use these as the region indicator, and this also helps to suppress noise in the indicator itself. So combining these, we have first of all a good initialization of the mean features, with which we can use to compute the segmentation with the variational method, and also we have indicator noise reduction built in. So here are some results for texture segmentation, where we produce state-of-the-art results on a texture segmentation benchmark that was published in ICPR for 2014. And also, I would like to show you some crystal segmentation results. This is the application I'm most interested in, where we find if we use local Fourier windows, so FFT applied to local windows of the image to extract features, this works extremely well even on very noisy data. And also this allows us to have unsupervised features, so the other competing methods for crystal segmentation all use like stencils that require you to encode manually the geometry of the crystals.